Okay, so today's class will deal with entirely with the harmonic oscillator problem. So we had started with the operator formalism. So there are two ways to solve this problem. One is when you define certain very unique and new operators, and then you use them, and this is a method of solution that you have probably not encountered before. And then after that, there is, of course, the ordinary differential equation solution. And the point of showing you both is to show you how much the operator formalism simplifies things. Okay. So what we did was first that we okay,
But we
so
don't have a closed form expression for psi n. I mean, exactly. It's just that I mean, we haven't computed a dagger n psi 0. I mean, like that.
yeah, so the psi 0 was still solved from the differential equation, but this was a very simple first order differential equation. So I think we did it the
Yeah,
previous
ma'am, that
class.
was solved. I am saying for psi n. I mean, the expression that is written in form of the operator, but not in a closed form. I mean, we haven't acted the operator yet. I mean, a dagger n is just left like that.
No, I mean, if you keep operating it, you get 1 by n factorial, root of n factorial psi 0 n. Psi 0, sorry. You do have a closed form of that. Didn't I write
No,
it
no, ma'am.
before?
We get the I got the this thing, the normalization constant. I'm saying this thing. A dagger n just
Wait, let's see.
is left.
You mean, yeah, you mean this is left? But you can act. You can actually act this a dagger every time. So you know the action of a dagger on psi 0. So every time
Yes.
it gives root of 1 by root of n minus 1. Okay, I haven't. Have I not shown that to you? Let me do that also. Just one minute. Okay, so we'll do a little bit more, and then I'll show you how you can get the functional form of psi n as well. I mean, without any operators remaining. So okay, so I'll just go through the what we did before as a recap, because it's many steps and it's easy to forget what's happening. So we started the harmonic oscillator problem. And we used the classical energy expression in terms of the momentum and the potential. Then we replaced the classical momentum with the operator for momentum, as you usually do. And then we defined certain operators after factorizing the Hamiltonian into two complex factors. Then we define these operators as V dagger V. And then to simplify our algebra in the future, we went over to A dagger A, which was simply multiplying some constant with V so that the commutator of these two new operators became 1 rather than some non-zero value like here for the V's. And once we did that, we got a simple Hamiltonian which involved H cross omega A dagger A and a number. So basically, these operators give you an additional number in the energy always, okay, which doesn't depend on the wave function. So it's a constant shift, and this we call the 0-point energy. So the minimum energy that the harmonic oscillator system can have became a constant value. So it was not zero, or you couldn't shift it around as you like. Then these operators were found to have certain properties. like they reduced the energy of a given, so A reduced the energy of a given wave function by h cross omega. A dagger increased the energy of the wave function by h cross omega. And using this, we generate excited states from a given ground state. To find the ground state, however, we have to still solve a differential equation to get the functional form of the ground state. But this is a much simpler equation which only involves the first derivative, and we directly solve that to get psi 0. Yeah, and the functional form of psi 0, that is just like a normal wave function. It's a Gaussian wave function, if you know what that means. It's e to the power minus some constant into x squared. And then when you act the so-called creation or step-up operators, it takes you from the ground state to the first, second, third, etc. excited states. Okay. And then in order to have some practice about how to handle these operators, we did a few exercises about the commutators of these operators, then products of these operators, and what their action on wave functions are. So we saw that the first and most important thing is AA dagger equal to 1. And then we defined something called a number operator, which was A dagger A. And we saw that A dagger A gives you an eigenvalue of n when it acts on psi n, which means it tells you the which excited state you're acting the operator on. Okay. Then we found out some commutators with strings of creation annihilation operators. So A with a string of k A daggers. Then we did A dagger with a string of A operators. And then the number operator with the annihilation operator and the number operator with the creation operator. Now the other two relations where we stopped was number operator with a string of annihilation operators and the number operator with a string of creation operators. So we'll start there today. It's lecture 16 today. Today is October 5th. So first we'll show the commutator of n with a power k. We want to show that it is k multiplied with a string of k operators. So what this, so why this is important? So basically then, if you take a commutator of the number operator with a string of operators, it tells you how many operators are there in the string, because the eigenvalue is k when the length of the string is k. So this has some importance in using these operators in actual problems. So that's why we do it. I mean, it's still not, I'm sure it's still not clear to you why taking commutators with strings of operators are useful, but you'll see why it's useful. So just think of this as an exercise for now. So what is the proof? So let's do the first one. So I'm not writing the hats. It's a bit tedious to write it all the time. Okay. So then again, we use the commutator over here to shift A to the left. this is plus E. So then again we'll apply it over here. So we'll take 1a from the a to the power k. So we have a. Okay, I'll write one more step. A into a. We'll apply it over here. So multiplying a minus 1 and a to the power k minus 1, I get another minus a to the power k. Then the remaining terms. So I get minus 2 a to the power k. This is a square. Wait, a dagger. This also has a to the power k minus 1. A square, a dagger, a to the power k minus 1 minus a to the power k, a dagger, a. Okay. Now if I do the same thing, by taking another a out from here, then I guess you can see that this will become another a to the power k, so minus 3 a to the power k, and I will be left with a cube, a dagger, a to the power k minus 2. Okay. And you can continue now like this till such time as you get k a to the power k, which means that my power on this a will become k now. And I will exhaust all the a's from this string of a's in this term. So I will have a k, a dagger, sorry, and then I'll have 1 left. So this is 2, right? So when this is 3, this is 3, this is 3, and this is 2. So I will still have 1 a left over here. And then these two terms become the same. So I can cancel them. Okay. So is this clear to you? So it's basically a repeat of the same thing, that you take out 1a from the second term and then apply the commutator, and you collect all the a to the power k terms, and eventually you end up with k of them, and the remaining 2 terms cancel. The proof of with the a dagger to the power k is also similar. So I guess you will be able to do that. It shouldn't be a problem. Now let's see how we can apply this. Let's see. So what is the significance of n then? Then n acting on a string of creation and annihilation operators tells us how many operators there are. Therefore, N is called a number operator. Okay. So, the next thing that I want to talk about is the normalization of the excited states when we are generating them with operators. So I did not probably show you how the normalization came about last time. So first, of course, there is the ground state psi 0. And that we have defined to be normalized. So when we solved the differential equation, then itself we enforced the normalization condition and we got psi 0 to be normalized. Then once we know psi 0 is normalized, is psi 1 normalized? So is the overlap of psi 1 with itself equal to, well, what is it equal to, let's say? And let's try working that out. So this is a dagger on psi 0, a dagger on psi 0. Now whenever you have these sort of functions generated with operators, the idea is to get the psi zeros to the extreme left and right and have all the creation and annihilation operators as a string in the middle. And once you have it in a string, then you can simplify it, knowing the relations between these operators. So what we will do is we will keep the psi 0 in the bra part and take a dagger to the ket. And when I do that, of course, a dagger will change to A. So I will have A dagger psi 0. Okay. And now, since I know that action of A on psi 0 is 0, I can add or rather subtract a dagger A from psi 0 without any problem. So the action of a dagger A on psi 0 is equal to 0. So it doesn't matter that I put it in. Okay.
Ma'am,
Psi 0. Yeah.
ma'am, could you please show how you went to the second step from the first one? I couldn't understand that.
So when you shift things from the bra to the ket, you do a dagger. So that's what, and then so from here to here, what we have done is, so a dagger of a dagger is A. And when you go, so the bra function is basically, if you convert it to a ket, if you have any function x, that is x dagger. This is part of Dirac's bracket notation.
Okay, ma'am.
Ma'am, can you please
Does
just go a bit upward for just for a second?
further?
Ma'am, yes, ma'am, a bit more. Uh, yes, ma'am. Yes, no, ma'am, down. That Pada one. I didn't.
The which dagger one?
Uh, yes, ma'am. Done. Thank you.
Done. Okay.
Yes.
So okay. So we generated the commutator over here, and we know that the value of the commutator is 1. So then I end up with psi 0, which is 1. So the excited state psi 1, first excited state, that is also normalized. Okay. But that is not enough. Let's go to the next one. I want to verify the second excited state as well. what is the value of the overlap. Sorry, excuse me. Okay. Psi 2 is equal to, I have two A daggers, psi 0, the same function here. I do the same thing, so the A daggers become A from when going from bra to ket. Okay. And I can introduce
You can just relate with psi 1, right? I mean, it will just be psi 1, normalization of psi 1 if we repeat the exact same steps as before.
unfortunately, it will not be, but so I can tell you psi 2 will not turn out to be normalized. So that is the problem. So let's see. Let me just do this, then we can try it with psi 1 if you like. So, okay, so I introduced another term whose action on psi 0 is 0. So I have a commutator of A with A dagger square. Psi 0. And if you remember what the commutator of A was with A dagger to the power K, it was K A dagger. So this commutator has the value 2 A dagger. Psi 0. And then you have 2 psi 0 A dagger, and I can again introduce A dagger A psi 0. That is equal to 2 psi 0 commutator A dagger psi 0. This is 1, so I have a value of 2. Okay. Now, why you couldn't do psi 1, I can tell you in one sentence. That is because
And that a psi 0 equal to 0, that thing we cannot
yeah,
use.
that thing you cannot use. Exactly. So that's why you cannot do it with psi 1. You have to go all the way to psi 0. So this is 2. So this is not normalized. So then let's call these psi 2 prime. And then I can write the normalized psi 2 then. And this will be 1 by root 2 psi 2 prime. Similarly, if you had if I wrote it generally as A dagger, so this string, if I wrote it as n number of A daggers for psi n, then you will get the overlap of psi n prime. Oh, that's not scrolling. So if I do psi n prime, psi n prime, I will end up with n. Therefore, in general, psi n will be equal to 1 by root of, you will end up with n factorial. So you will end up with n factorial A dagger to the power n. Oh, sorry, I'm very sorry. Shouldn't have written it like this. This will still be n. Okay. So psi n will be normalized by 1 by root of n factorial psi n prime. But then if you want to write this, you will get A dagger to the power n psi 0. Okay. Or what did I do wrong? Sorry.
Ma'am, if we are
No,
writing
no, no,
this
no, no,
equal
no.
to n, so
No, no, no. Sorry. Yeah, so this is n. So we would get 2. So if I generalize this, what would I get? If I had 3 of them, then I will get 2, and then I will have 2 A's, and then yeah, I will get n factorial when I do this directly. Yeah, because every time, so here we directly finished off with AA dagger equal to 1. But if I had one more A dagger, then I would get A dagger Q. Yes. Oh yeah, I would have got an A dagger square over here. If I had a cube here, then I would have got an A dagger square over here. So I would have to repeat this process one more time. And then I would get another 2 from that. Do you get it? What happened? So the commutator of A with A dagger to the power K, that is equal to K A dagger to the power K minus 1. So here I got from square I got A dagger, but if it was A dagger cube, I would get A dagger square over here. So I would have to do one more step before I got the commutator of A dagger. Okay, so that's why we will get 3 into 2 if I do for psi 3. And then for psi n, I will get then n factorial. Okay. You can try it for psi 3 and you'll see that it is 6 and not 3. Then this was the normalization. So they're normalized. And the next thing, is there any other algebra that we need to finish? What else? Okay, no, I think this is about it covers more or less the important
Expression for psi n, you said you will derive.
Oh, the expression for psi n. Yeah, yes. 1 minute. So expression for psi n. So let's do something. So the expression for psi n, I think, is better described after we do the differential equation method of solution. Okay? Because I need to introduce Hermite polynomials before I can give you the functional form. So we'll do it at the end of the class if we manage to finish the whole thing. Otherwise, it will be on Thursday then. So okay, so this was about the operator formulation. Now let's go to the Now we'll do the differential equation method of solving the harmonic oscillator problem. It is also called the power series method. It's also okay. it's also called the Frobenius method. Fine. So now we have to go back to the Hamiltonian and the Schrodinger equation. So H psi equal to E psi. And now we will just stick to writing it in the standard differential equation form. Okay. And I will move the 2's to the right. So this will be a bit tedious, okay? So you'd have to be patient. It's not nice and neat like the operators. Now I divide by H cross omega. And I get H cross by M omega.
Isn't there a psi multiplied to half m omega square x square?
Yes, 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 yes. Of course, there is. Sorry, no.
Not the whole
Just,
bracket, right?
no. It should just be this one. Okay. And then by H cross omega, so I get this. Psi 2 E by psi. Okay. So now we'll do some change of variables. So we will go to from x we'll go to psi. This is just to get the equation into some sort of more simple looking form. So then psi is this, which means x is h cross m psi, which means dx is equal to root of h cross psi m d psi. Okay.
Is that to
Now we
get
have
the
to
middle
evaluate.
term to be 1?
It's to get to remove the constants basically.
Okay, so from the middle term, right? I mean that m omega x square by h cross.
Yeah, we are guessing from that term, yes. And we divide it by h cross omega to make it sort of dimensionless in a way. Because energy and h cross omega have the same units. So it became dimensionless, and now we go over to some variable where the constants are removed. D psi. Okay, so now we have to evaluate the second derivative. So let's see what that looks like. D psi dx is now. So it's the reverse of this. So root of m omega by h cross d psi. And that is equal to cross d psi of d psi. Okay, so we got the form of the second differential of psi, and now we can write the equation again. back to the Schrodinger equation. So we have this, and then it cancels with this factor. So h cross by m omega on the first term cancels with m omega by h cross from the second differential, and I end up with minus d square psi square. And from the second term, I have x squared. So x squared will also give me h cross by m omega, which will cancel with the factor here. So I get simply psi squared. Psi. And on the right, I have 2e by h cross omega, which I write simply as some constant k psi, where k is equal to 2e by. So then this starts looking a bit simpler. So the equation that I want to solve now is then d square psi d psi square is equal to psi square minus k psi. Okay. So then the goal of the equation is to find the energy E and the wave function psi. So and that translates to basically finding k and psi in this equation. Okay. Now, like we do for differential equations, we have to guess the form of the solution. Okay. Now, to do that, let's try to guess the form of the solution. Okay. The first limiting case that we look at is for very large x. So we are thinking of the tails of the wave function. So when x is very large, which means that xi is very large. And in that case, you can ignore k in relation to xi square. So xi square is very much greater than k. This is capital K in case. Therefore, d squared psi d psi square is now approximately equal to xi square psi. So this is one more advantage of going over to a dimensionless equation, because if you have terms with different dimensions, then it becomes difficult to do these boundary arguments. But here, the whole equation is dimensionless, so terms in it you can simply compare the numerical value as such without any problem. Okay, and this is again a standard form of differential equation, and we know the solution, which is psi is equal to a e to the power minus xi squared by 2 plus b e to the power plus xi squared by 2. Okay. Now, every time we do a quantum mechanical problem, we have to always keep in mind the normalization. And as soon as we look at this, we see that when psi tends to infinity, plus infinity, then although the first one will decay to 0, the second will blow up. And if psi tends to minus infinity, then the first one will blow up and the second one will decay. So this solution is certainly not normalizable from minus infinity to
Ma'am,
plus.
how did we get this solution? I did not understand. I mean, you just wrote it down.
Oh yeah, this is a standard differential form, so I just wrote it down. But you can, this is just a normal mathematical solution. So you integrate everything 2 times and you will get this. So we did it for a minus xi square. This is similar to the plus xi square as well. You can just look it up in a maths thing, because if I do it now, then it will take quite a lot of time. But as it is today, we'll have to do a lot of things. I'm just using a standard result. So this is using a standard result. I didn't do anything special. So what you do is basically from here, because this whole thing will never be normalizable, you say that, so this is the general solution, but it also means that half of it, like just the first term is also a solution and the second term is also a solution. So in this case, the general solution is not applicable and we have to choose one. But I said something a little bit inaccurate. So I'm sorry, I said something a little bit wrong. I said that the first one will blow up when xi tends to minus infinity, but that's not true. We have xi square, right? So it's always the second one which will blow up every time. This one will blow up for xi going to infinity or minus infinity, because it's xi square. So so second one is never valid. So we know it's only the first one which can be valid. Okay. So I was not careful. I hope you got that. Okay. So we have to choose one. Choose the one which is normalizable. So the valid solution in this case is psi is equal to a to the power e minus xi squared by 2. But this is then the solution for large x or xi. This is only a limiting solution. It's not the solution over the entire range of x. So what we have got is the what you call the asymptotic function. Okay. Now then, from this asymptotic function, we make a guess about the general function. So we suggest that the solution of the differential equation over over all x, let's say, over all x has the form psi xi is equal to some function of xi multiplied by this asymptotic part. Now this is again something that is done in quantum mechanics, where you guess the form of xi or look for a certain form of xi, and then the guess that you start out with is called an Ansatz. This is a German word which is a guess for the form of a wave function. Okay. Now, generally, an Ansatz is general enough to give you any solution. Okay. But you're taking a particular form so that the solution of your Schrodinger equation becomes easier. Okay. So, in this case, it's general enough because I multiplied it with an arbitrary polynomial function. So this is an arbitrary polynomial function. Okay. So this covers any solutions that you can access with any equation. It's a perfectly general function. But I am taking it in this sort of factorized form with an exponential because I expect that this will lead to a simplification of the solution method. Okay. Now this is again a wise after the event ansatz. So people must have tried many ansatz and they did not end up being able to solve the differential equation. Okay. And finally they hit upon this where they could. Yes?
Ma'am, like, how can we take it as a polynomial? Like, would it be just simply powers of xi, like xi
Yeah,
squared?
powers of that. Yeah.
So, at large values of xi, it should reduce to e to the power minus xi squared by 2, right? So,
Yes.
if it is polynomial, it will just blow up. It won't reduce to the e to the power minus xi squared by 2.
So we will use that argument. You are very close to the answer actually. So the argument will be that this h psi, it will have to be a finite polynomial. So that eventually it becomes insignificant compared to the exponential.
Okay, so relatively, exponential will be larger than this one, you're saying.
Relatively, the exponential part will dominate when xi is large.
Okay.
And that part we have seen decays with large psi. So it will finally damp out the polynomial part. So that is the expectation of doing this. But this has come after a lot of struggle. Okay, it's not like people just saw this equation and figured out that this is what the ansatz or guess should be. We are just going via the path which has already been cleared for us. So that's why you do standard problems. If you're just given an arbitrary quantum mechanics problem to solve, and if you're even given, I don't know, 2 months to do it, it's very likely that you will not find a solution. Because there are so many pathways to adopt and only a few will actually give you the something that is solvable. Okay, so this is sort of the guess or the form of the function that we use. And h is, I'll write it explicitly, it's some polynomial in xi. Okay. And I can write it concisely as a summation. So you see, if we had even taken just h psi, that is also a general enough function for me to start with. But we're using this exponential factorization from a limiting case because we're hoping that then I will get a finite h psi and that will give me a neater solution. So let's put it back in this equation. So the first thing we'll need, of course, is the first derivative of this psi form. First thing we'll do is take a first derivative. And that is d psi. That's from the first term. And from the second term, we get minus 2 psi by 2 h. first derivative. Now the second derivative. Okay, so the first term is this dh d psi multiplied with exponential. So I'll keep the exponential outside. Because I'll always get it. And then from the first term, I'll get d squared h d psi squared. And when I take a derivative of the exponential, I will get d psi multiplied with, again, so this will be what did I do? So this one, this is minus 2 psi by 2. No, this was, oh, this is, sorry, this is plus this. Okay, so this was the first term. Then we have to do the second term. This is the first one. Then we have to do the second one. That is a minus sign. And I have d psi h multiplied by 1 minus I squared by 2. Then I have plus psi h was already there, plus 2 psi by 2 minus I squared by 2. That is equal to d squared h d psi squared minus dh d psi to the power minus I squared by 2 minus d d psi. So I have h, and then I have another minus of psi square h multiplied with 2 minus psi squared by 2. Okay. Then simplify this little bit more, maybe d squared h d psi squared minus 2 psi. No, wait, what happened? So this was 2. Did I miss something? Oh, I have missed a psi here. Psi here. This. Wait a minute. So there should be 2 of them. Did I get that? H. Psi H. Must have made a mistake somewhere. Wait a minute. dh d psi, we have one term here. Oh, okay. So there's one more term here, is it? Yes. So this is here. So d d psi is h, and then you have another one. So I missed a term here. Sorry. So when I do this, so once I have h, And I also have xi into dh d psi. Yeah, so then I'll get 2 over here. Plus xi square minus 1 h e to the power minus xi square by 2. Okay. So therefore, I can now write the Schrodinger equation as d squared h d psi square minus 2 xi dh d psi plus xi square minus 1 h e to the power minus xi square by 2 is equal to, if you remember the right hand side, it was xi square minus k e to the power minus xi square by 2. Okay? So we can delete the exponentials from either side. And we end up with an equation only for h. Okay, I can simplify this a little bit more. Xi square h from either side, which can be cancelled. So I am only left with k minus 1 into h. Okay. This is equal to 0. So now this looks like a more tractable equation. At least we only have h, which needs to be found out. But now we have to evaluate these derivatives as well. So we know the form of h, so let's do that. So we have to evaluate dh d psi, which is basically d d psi of this full of the series. Remember, I wrote h as a series, which is basically just a concise form of the polynomial. And when you do that, you will get infinity aj j psi to the power j minus 1. Okay? Then the next thing is d squared h d psi square. And that is now d d psi j to the power j minus 1. That is equal to sum j equal to 0 to infinity aj j into j minus 1 psi to the power j minus 2. Okay. Now we will do a trick. That is, what we want to do is we want to have xi to the power j instead of xi to the power j minus 1 in this expression. And we can shift the indices because this is a series, infinite series. So let's say I go over to j prime, which is equal to j minus 2. Then my j prime will go from minus 2 to infinity. And I will end up with j prime plus 2 over here, and then I have j prime plus 2 into j prime plus 1 into xi to the power j prime. Why is it not scrolling? What happened? This one will now. So this is fine. And then I can change back to j, because these are dummy indices, doesn't matter. Plus 2, plus 2, plus 1. Tablet doesn't want to scroll. It's, just 1 minute, it's not scrolling for some reason. Fine. This is J. Okay, now when what's wrong? It's not responding.
Ma'am, can you
Give
please
me a
bit
minute,
go
somehow my
upward?
just 1 minute. My tablet's not responding.
Oh, okay, ma'am.
Okay, yeah. Tell me.
Yes, ma'am.
It shouldn't be j equal to -2. It should be just j equal to 0. Indices should start from 2. Yes,
J
actually.
equal to -1.
In the series, I mean, j prime equal to 0. It should start from 0.
No, I am replacing j with j prime plus 2.
In the original series also, it shouldn't start from 0 because the first term itself is 0.
Yeah, so I will remove them. Yeah, you can do it at the beginning as well if you like. So yeah, this can be, oh no. So yeah. So the first two terms are 0. So if you put j equal to -2, this will become 0. If you put j equal to -1, also this will become 0. So you can write this. Yeah, so the first two terms are by construction 0. Okay, therefore the Schrodinger equation is now, so we have the second derivative, which is j plus 1 into j plus 2 into a j plus 2. Then you have the second term, which is 2aj, 2aj into j. J j plus k minus 1 into j multiplied by xi to the power j is equal to 0. So this is what I wanted to do basically. So I wanted to have xi to the power j in all the series, in the all three terms, so that I can take that common. Okay. So then I get a relation between the coefficients a. Now, since the coefficients of every power of xi should disappear, now coefficient of every power of xi must disappear. Therefore, I have the relation that j plus 1 into j plus 2 into aj plus 2. So what's in the bracket basically? 2jaj plus k minus 1aj. So this is equal to 0 for all j. Remember, xi is the variable, and if you have different powers of xi, they cannot, the terms cannot cancel among each other. So the coefficient of every power must be 0. And from this relation, I get a connection between the coefficient of the j plus 2th term with the jth term. So if you simplify this, I'll just write the relation now to save some time. 2j plus 1 minus k by j plus 1 into j plus 2 into aj. And when you relate the subsequent coefficients of a series with the previous coefficients, it is called a recursion formula. So you have come across them before. So it tells you how the coefficients of the various terms are related to each other. And so, since we are relating j plus 2 to j, it tells you that given a0, we can get a2, a4, a6, etc. And given a1, we get a3, a5, a7, etc. So the even powers of xi, the coefficients of the even powers of xi are related to each other, and the coefficients of the odd powers of xi are related to each other. So I can write the power series H psi as a sum of two series. One goes over even powers of psi and the other goes over the odd powers of psi. So I can split them up into two. Okay. Now knowing this, can we figure out something about the normalization? Let's see. Now we have to check normalization. So psi is h psi e to the power minus psi squared by 2. Okay. So let's see. So what is the form of AG? Can we figure out if the coefficient has some form which is directly related to J? So if J is very large, so for large J, which means for the last part, the last few terms of the series, let's say. So when J is very large, then if I say that AJ plus 2, AJ is some constant by J by 2 factorial, then this is consistent with the recursion relation. J is consistent with the recursion relation. Now this again I am just pulling out of the hat, so I'm sorry. So this this is something that people guessed.
But there are
through
gaps of 2,
intuition.
right? I mean, AJ plus 2 and AJ is the relation. So the middle terms will be missing, right, out of the factorial.
Uh, the middle terms are missing out of the factorial, meaning
Meaning there are gaps of 2 every time between the
no. So
coefficients.
this is for every j, right? So this is only one value of j. So this is like an even integer division of some constant.
Okay.
And if j is odd, let's say, then that so one part is ignored. So you only have, when you have j by 2 factorial and j is odd, then you have to ignore the remainder. So this is an integer division where you ignore the remainder. So let's say, so this is like in programming. So if you just divide an integer by an integer, then you store it in an integer, you only get the quotient and not the remainder. Even integer division. So you keep just the quotient here. So this is an, you can say, is consistent, or this is an approximate solution for the coefficient AJ, which is consistent with the recursion relation. So how is that? So I can show you the consistency, but unfortunately I am not able to justify how people figured this out. Okay. So I can show you the consistency. So let's see. So if AJ plus 2 is 2j plus 1 minus k by j plus 1 into j plus 2 AJ. Okay. So if j is large, then from the numerator I can ignore 1 minus k. So I get 2j. And in the denominator I get j squared AJ. That is basically 2 by j AJ. This is 2 by j AJ. Which means basically that AJ plus 2 by AJ is equal to 2 by j. So which means that the gap between the subsequent coefficients gets smaller and smaller as j increases. And from this guess also you see that AJ from the guessed solution you get AJ plus 2 by AJ is equal to j by 2 factorial by j plus 2 by 2 j plus 2 by 2 factorial, and that is equal to 1 by j by 2 and 1 by j by 2, which is equal to 2 by j. So they're consistent for large j. Now, how does that help me? So now I have an expression for AJ for large G. And this will help me. So consider the function e to the power y square. This is just a function. Then I can write this as a series where I sum from n equal to 0 to infinity. I have 1 by n factorial y to the power 2n. This is the series form of e to the power y square. And then this I can write as something as j, which goes from 0 to 4, etc. as j by 2 factorial y to the power g. Acceptable? So I've just gone from summing over all integers to just the even integers. And I've adjusted the terms in the series accordingly. And then this looks like aj y to the power j. Right. So now if this y is my xi, for example, then my h xi has the form e to the power xi square or large G. So this means that the last part of this power series starts looking like e to the power xi square. Now this is certainly not a normalizable function. So this will make psi unnormalized. Yeah?
I will become a constant. Right?
Sorry, I didn't get you. Can you repeat?
Ma'am, I said that psi will become a constant, right?
Psi will become a constant. No, it will not become constant. But what we showed was that this power series, even if it obeys the recursion relation, the last part diverges. The last part of the series, because it looks
Ma'am,
like
but it is multiplied by e to the power minus
chi square by 2.
Yes, yes.
Yeah.
Okay, so
Yeah, but that is again, yeah, it's chi square by 2, so it's slower than the last part. Yeah, or it is constant, yes. But then even if it is constant, since it is a summed up series, that last part will never reduce to 0. So the series will diverge. The last part, even if it becomes constant, even if you have 2 plus 2 plus 2 plus 2 going to infinity, that is also a divergent series. I mean, you cannot. It will not be normalizable. Yeah. So the only possibility now for this whole psi to be normalizable is if h truncates somewhere. So the recursion relation actually didn't help us to keep things normalized. The only way now that we can have a normalized psi is if h xi truncates at a finite power. Okay. So this is finally the crucial point, that it has to truncate at a finite power. Now, when can that happen? So let's look at the recursion relation once more. I hate this happening. Okay, this and this is divided by 2. Right. So if this is the case, then this can happen only if K is equal to 2j plus 1. So if K is equal to 2j plus 1, then for all j, or for all j beyond a point or whatever, then the aj plus 2 or all subsequent j's will become 0.
It should happen
So
only
then
for
we will
once.
have a, yeah?
It should happen just once, and then all subsequent will be zero.
Yeah, and then all subsequent ones will become 0, yes. So let's say it becomes, so I won't write j, then that confuses things. So if k is equal to 2n plus 1, let's say, then for j equal to n or j greater than equal to n, let's say, that is clearer, aj plus 2 is equal to 0. Okay. So if k has the form that is 2n plus 1, then for all j's which are greater than or equal to n, the coefficients will be 0 and I will have a finite h psi will be obtained. Okay. Now let's recall what k was. So k was basically an energy. It was 2e by h cross omega. K was defined as 2e by h cross omega. So this is an energy. Therefore, this means that if k has to be 2n plus 1, then E has to be 2n plus 1 by 2 h cross omega equal to n plus half. So now we end up with only certain allowed values of E. So now my energy can no longer be anything. It can only be n plus half times h cross omega. So this is the basically the quantization condition that we obtained earlier as well. So what happened here is that the requirement of normalizability quantized the energy of the system. So only when the energy of the system is is of the form n plus half h cross omega, we can get normalizable solutions for psi. Okay. Now, I have to tell you even a little bit more about that, because n can be even or n can be odd. And remember, h had two parts, even plus odd. So, if n is odd, then the truncates if n is even, then the even series truncates. Okay. The other part, but h psi is equal to h even psi plus h odd psi. So even if one part is normalizable, the other can still diverge, and you would still end up with a psi that doesn't that you can't normalize. So this condition of normalizability also means that there is an additional requirement that h psi is either even or odd. So this sum, the solution of h psi is a sum of even and odd, although that is what you would expect from the differential equation. The general solution again is not valid, and you only have solutions which are either even or odd. Okay, it's either even or odd, not a general combination as we had proposed before. So we discard the general solutions in favor of some specific ones. So just an even series is also a solution. Just an odd series is also a solution. So that's fine. It's not that they're not solutions, but the general one is not valid. So you only have either even solutions or odd solutions, and these solutions have energies which are of the form n plus half h cross omega. Okay. So here you see this quantization of energy. This entered from an entirely different perspective. So when we did the operators, then the quantization came from the fact that the step up and step down operators, or creation and annihilation operators, they could only change the energy of the states by half h cross omega. So the gaps became fixed when we did the operator solution. But the fact that energy is quantized comes from the requirement of normalizing the wave functions in case of the differential equation. So the sources are different, but the solution is the same. So we still get the same energy quantization condition and the same energy spectrum for the system. So this is very remarkable in quantum mechanics, that in spite of very different approaches, the final physical results are always the same. So it basically means that your mathematical formulations or how you tackle a problem is entirely up to you. So there is no unique internal mathematics. So you will see if you pursue quantum physics or quantum chemistry later on, and you go into more theoretical developments, that you are free to even formulate your own theorems and own mathematical techniques as long as they respect certain broad requirements that you know about the system. Okay. Such as this normalization, quantization, or energy, or if you're doing very a real system, then the experiments that you do on the system. So the mathematics you can invent. So that is really amazing.
I had just one question.
Yeah.
That for the infinite well, there we saw that only psi is continuous over all x. The derivative is not. But here, when the ladder operators and the power series is used, we are assuming that psi is, I mean, differentiable any number of times we want. So how is
Yes.
that? I mean, allowed? I guess. I mean, how can we directly assume that?
So here the form we have assumed is differentiable cross n. So we assumed an infinite series multiplied by an exponential, so that taking derivatives is not a problem on that function, because the form is general enough. And what you say about the particle in an infinite well, so the derivative is, it exists. It's just that at the boundaries, they get killed, the wave function. So in the domain of the problem, it's fine. And here actually the potential is also infinite. Potential, it has to form half kx plus. So
Okay,
valid
because
from
I
minus
was
infinity to plus infinity. So there in 1D box, the potential
okay,
itself
so
had a domain. Here it is minus infinity to plus infinity. So that's why
okay, ma'am.
things
Because I
have to
just
be
wanted to ask that
construed. Yeah, continue, sorry.
okay, because my question was that, I mean, we assume the form of a power series times an exponential to begin with. So can there exist solutions which are not of this form, which will, I mean, which will not get because of this method essentially?
So here, because you have that exponential, it remains differentiable. If it was just the power series, so what would happen is the wave function, the derivatives would exist up to a point, and after that they would become zero. But it's not like the function is discontinuous over for some values of xi or x. That is never true. I mean, the differentiability, it's, so let's say if I have if I just had a wave function which was x, then you only have the first derivative, and then there is no further derivative. But that is not a problem. Having all derivatives is not necessary.
No, ma'am, I mean, zero is still differentiable. By non-differentiable, I mean,
No, see, the problem would arise if you had
hello, ma'am.
certain values of x for which this was not differentiable. So that is what quantum mechanics doesn't want you to do. So if you had something like 1 by x minus 1, and the domain of your function is from minus 5 to plus 5, then you have a discontinuity at x equal to 1, which is in the domain of your function. That is not enough.
Okay, ma'am. Because I mean, for psi, I understand that there cannot be a discontinuity and it must be differentiable everywhere. That I understand. What
Yeah,
I mean to
okay.
say, even for the successive derivatives, how that is holding. That is my actual question. I mean, the same
How that
condition
is
for psi.
no, that is not a requirement of quantum mechanics.
Okay.
But since the Hamiltonian involves the second derivative, your wave function will at least have to be differentiable up to the second derivative. Otherwise, you will not have
Yes, yes.
energy there. But but it is not something that is required
Okay.
by quantum mechanics.
Okay.
Okay, so then here we obtained the energy. We are still left to determine the wave function. And for that again, I will make a jump and tell you about something that is very fascinating, again, for physicists and chemists, that mathematicians have already found solutions for things without knowing what they would be useful for. Okay, and this recursion relation, if you gave it to a mathematician, they would tell you that there is a set of polynomials called Hermite polynomials which satisfy this recursion relation. Now, don't ask me how they figured it out. They have developed this from just an arbitrary recursion relation. So they didn't get it out of a physical problem. They just found solutions to various things, and they happen to be useful in our case. So let's do the wave functions now. So wave functions which or polynomials which satisfy the recursion relation are the set of Hermite polynomials. And these were discovered or invented, whatever you like to say, much before the harmonic oscillator problem was solved or even tackled. So once you got this recursion relation, you look back at mathematical literature or some mathematician told you, they saw the relation and told you we have solutions to this. And this was the set of Hermite polynomials, which was done by Hermite, I guess. And then this has this, the set looks like this. So given an n, okay, let me do this a little bit better. So we have aj plus 2 equal to 2j plus 1 minus k by j plus 1 into j plus 2 aj. Okay. Now I can put k equal to 2n plus 1, which basically tells me that I am dealing with a state with energy En. I am labeling the energy now by a quantum number n because I have found that this energy depends on n, so I can write that this is En. And these Ens are basically the various energy states. So you have E0, E1, E2, ground excited states, ground and excited states. So let me write k equal to n minus 1, then aj plus 2 is equal to 2n plus 1, so I can take minus 2 common. I have n minus j, then I have j plus 1, j plus 2, aj. Okay. So given a certain value of n, my allowed values of j will go up to that n. So n, j, then hn. Hn psi, psi n psi. So let's say my n is 0, so that's the ground state. Then you only have j equal to 0, and hn psi has only a0, and psi n psi then will look like a0 into e to the power minus z squared by 2. That is simple enough.
Ma'am, can you please just go up or a little bit?
More?
No, ma'am. I'm down. Yes, ma'am. Okay. Thank you, ma'am. Done.
Okay. Then when n is 1, so the first excited state, then you have just 1. Remember, you can only have either even or odd. So j is only 1. Then you have a1 and there's xi to the power j. So here you have a xi in the hn function. Then this looks like a1 xi to the power minus xi. Okay. Now when n is 2, now you get the first sort of non-trivial one. So that's 0 and 2. So you have a0. And then you have minus. So what you would have is a2 xi squared, and a2 is equal to 2a0 xi squared. So this is a0 into 1 minus 2 xi square e to the power minus xi square by 2. Then for 3, you have 1 and 3. This is a1 psi minus 2 by 3. So what I'm doing here is basically I am putting in the value of n and j in this recursion relation to get these factors. So I haven't identified the Hermite polynomials yet. So this is Q and then a1 psi common 1 minus 2 by 3 psi squared e to the power minus x squared. Okay, and then you can go on and it gets increasingly more complicated. And then the Hermite polynomials. So these so what you get, so let me just write the Hermite polynomials first. Then I'll tell you how to relate them. So you have the Hermite polynomials. And in the mathematical literature, they look like this. So H0 is 1, H1 is 2 xi, H2 is 4 xi squared minus 2, H3 is equal to 8 xi cubed minus 12 xi, H4 is equal to 16 xi to the power 4 plus 8 xi squared plus 12, H5 equal to 32 xi to the power 5, 16 xi cubed plus 20 xi, etc. Okay. So why do their polynomials look a little bit different than ours? So they had adopted the convention, so the mathematical convention for the mathematicians was that the coefficient of the highest power of xi is 2 to the power n. So this was their convention. So for H0 you had 2 to the power 0, for H1 you had 2 to the power 1, H2 you had 2 to the power 2. Okay. So that is what they had proposed in their mathematical formulation. Then they didn't know anything about the harmonic oscillator. So, but they follow the same recursion relation as the harmonic oscillator problem. Okay. So then, when we write our wave function in terms of the Hermite polynomials, then if we incorporate this convention in our wave function, then we can write psi nx as so you have this was the ground state. This was the ground state with the size here. Okay. And for every excited state, we had 1 by root of n factorial. Okay. This was what we had got before for psi 0. And then for the excited states, we have this incorporate the 2 to the power n that comes from the Hermite polynomial, and we can multiply it with h and psi. So this is what we got directly from our Schrodinger equation. And if we want to now write this as in terms of the Hermite polynomials, we have to divide them by this 2 to the power n, and then we can write them as harmonic polynomials.
Is 2 to the power n inside the square or outside the square?
Well, this is inside, so I can, let me see how I can maybe show it to you as well. Okay, now I'll relate it to what we had got before, so then it will become clear. Yeah, it's inside, it's not a mistake. So, we had got, so do we have some time? Okay, we have 5 minutes. So earlier, what we had was psi n x is equal to 1 by root of n factorial a dagger to the power n psi 0 x. And then this was 1 by root of n factorial a dagger to the power n. This we got from the normalization of the ground state. Minus m omega by 2 cross x. Okay. Now, a dagger is equal to root of m omega by 2h cross x minus I e by m omega. Okay. This is equal to root of m omega by 2h cross x minus. So now I'm writing the operator form of p. So I get minus h cross by m omega. So the I goes away. X. So a dagger
It will become plus, right?
So a dagger was minus, and then p is minus IH cross. So you have plus I square, so that's minus.
Okay, sir.
Yeah. So a dagger to the power n is simply m omega by, oh, why did I take any? 2h cross. This is to the power n by 2 x minus h cross by m omega dx to the power n. Okay, so this is m omega by 2h cross n by 2. What are we doing here? Okay, now we are going to xi. So do you remember what xi was? Xi was probably h cross by m omega root. So I can write this as to the power half xi. Then this is again h cross by m omega. And dt xi means the reverse. So I have m omega by h to the power half dt psi n. This is equal to omega by 2h cross 2. Okay. I can take now h cross by m omega to the power n by 2 common from here. So I have h cross by m omega by 2 common, which means that I have psi minus dt psi left over here to the power n. And now I can cancel h cross and and I am left with 1 by. Oh, sorry. I think my pen ran out of charge. So I guess you can see that. So you will get, I'll complete it and send it to you before I upload it. My pencil ran out of charge. So this is 1 by root of 2 to the power n. You get that from this first factor. And then you have xi minus dd xi whole to the power n. Okay. And this is if I can finish this. So 1 by, okay, it's writing again. 1 by 2 to the power n xi minus ddx to the power n. Okay. So therefore, psi n xi looks like 1 by root 2 to the power n factorial and omega by pi h cross psi minus d d psi to the power n minus psi squared by 2. Okay. And then there is again something that the mathematicians have told us, that there is something called the Rodriguez formula. Okay, which tells you that a Hermite polynomial can be written as an operator on e to the power minus psi square by 2. So this is the Rodriguez formula, and when you apply that over here, you can see that you will be able to generate a Hermite polynomial from this wave function. So it's still not perfect. I mean, here you have xi minus dd xi, and here you have just dd xi. But you have to work it out with certain more relations of the Hermite polynomials. So we're out of time today, so I'll complete it on Thursday then. But you get the picture. I mean, we're going in the right direction. We are almost there.
Ma'am,
Yeah.
ma'am, actually, could you please tell from where we are getting that 1 by 4 in the power part?
Oh, this 1 by 4 came from our normalization of the psi 0 that we had before.
Oh,
So I
okay.
put in, so I evaluated a dagger n basically, and then I put it back into this expression.
Okay, ma'am, got it. Thank you, ma'am.
Yeah. But we're still not there. I mean, this still does not look exactly like the expression with the Hermite polynomial. So we'll do a few more steps on Thursday. And I'll upload an assignment by tomorrow, which you need to submit after the autumn break. Okay. So thank you.
Ma'am,
Yeah.
ma'am, could you please upload today's recording? Actually, my internet was very unstable today. I could not attend the full class.
Okay. I'll upload it as soon as it's